talk for today is focusing a bit on a different angle on grid forming control that we've been developing in the last maybe 2 years, and basically has two parts. One is about what I would call a more universal control paradigm than what we have now, and the second bit will focus around challenges that come up when you think about protection of inverter interface resources. And before jumping into the details, one of the things that I wanted to point out, and that is also a key motivation for this consortium effort, is that there are no really clear or precise definitions of what we mean by grid forming control. So if you look in the literature, one of the earliest definitions here will basically say, oh, a grid forming converter is basically an AC voltage source that goes at the nominal frequency and magnitude. So by that definition, even the large scale power station would not be grid forming. So you can immediately kind of see the problems with this. Other definitions have emerged that focus on the ability to smooth the frequency. And then for grid following, the definitions are equally vague. So something you will often see in the literature is that we define a grid following converter as an AC current source with a constant power injection. But then even the standard, grid following control with a phase lock loop can actually not induce that behavior here under all situations. So let's say this is being quite generous actually to the PLL-based grid following control that we have right now. Some other definitions, they center around whether or not the phase lock loop is present. And that's again problematic because there are actually grid forming controls out there that use phase lock loops in auxiliary controls that are not, super important for the control law as such. But there's a phase lock loop present still. We would probably all agree on these things being grid forming. So to sidestep that issue, I would propose to take a slightly different perspective on this. And this is very similar to also what we've already seen last week when Deepak Diwan was talking about this. And instead of talking about, is this grid forming, is it grid following, we should set a few principles as to what do we want from inverter-based resources going forward to be kind of good citizens on the grid. And here's what I'm going to use as principles for this talk. First of all, the inverter-based resources should support the grid to the best of their ability. And by this, I mean, they should create a voltage with a well-defined and stable frequency and voltage magnitude. They should autonomously be sharing load while accounting for the source and converter limits. And they should somehow either dampen or at least not excite the fast dynamics. So this is this property that Deepak was talking about a week ago. And we have also done quite some work on this last point here, but I'm not going to talk about it today. And then the final point that I would like to highlight is that these controllers, they should be as simple as possible. And the reason for this is that if you make very complicated control laws locally, you will have a very hard time analyzing and understanding the behavior when you network millions of them. And there are a few grid forming controls out there that, they have like 25 tunable parameters. And I'm not convinced that, let's say, the tiny bit of performance gain that you may be getting from this is worth introducing all of that complexity. So that's the principles for this talk. And then let's see where that takes us. And before going into detail on the control, what I want to talk about here is just why do we even need the grid following control in the first place? And there are many grid following controls that you will see in the literature that ultimately end up providing some kind of support to the grid. And it's not quite clear why you would use grid following control for this. The one use case in which, as of today, you need kind of the standard grid following control architecture with the phase lock loop here. So basically you assume the AC grid is just an infinite bus. You have this creating a sine wave with a perfect frequency and magnitude. You have this phase lock loop here locking onto it, and then you control the power converter basically as a current source feeding into the grid. The one situation where you need this on today's system is if you want to do maximum power point tracking for renewables. I'm using PV as an example here, but similar ideas apply to, for instance, to wind power. And the gist here is that you're controlling the power injection into the AC grid, basically to stabilize the voltage here on the DC side that is seen by your PV panel to track the point where it generates the maximum power. And for the purpose of this talk here, let me call these type of control AC grid following, but DC grid forming, because what they actually do is they require a stiff and stable system here to lock onto that basically external devices that stabilize the voltage on the AC terminal of the converter. And then it's feeding any amount of power that it wants to stabilize the voltage on the DC side of the converter to track the maximum power point, let's say in this PV setting here. And as I said, for wind turbines, it's a fairly similar idea. So basically, it's not only that you're not supporting the grid, but you're actively relying on the grid to be able to basically create any power flow that you want here, to be able to stabilize the voltage here on the DC side. Then the converse paradigm, as we have seen many times in talks here in the seminars, then of course the grid forming control. And the hallmark here is that you basically in the control design, you ignore the power source that is feeding the power converter, let's say be it a battery, PV, or wind. And you're basically treating the power converter as a controllable AC source, where you measure the power flowing into the system, but you somehow adjust the phase angle and the magnitude of the voltage here. And as we've seen many times, one of these examples, for instance, would be group control. And the assumption here that is often not very clearly stated in the literature is that the same as we were seeing an AC infinite bus before for the grid following control, basically all of these designs that are based kind of on these types of dynamics here that kind of roughly encode group control, they all assume that the DC voltage here is infinite. So you have your DC AC converter taking some DC and modulating it into AC. And all of them basically ignore that this voltage here is not constant. So here we have the opposite assumption that the DC grid or DC terminal of the converter is an infinite bus. And we control the AC side of the converter to create a stable AC voltage. Another thing that is typically neglected here in this design are converter current limits. And this is what we will be talking about when we talk about protection. And the objective here is not to extract maximum power from a renewable source behind here, but really to stabilize the AC network. And if you kind of want to capture this more accurately, then again, for the purpose of this talk here, we call these types of controls AC grid forming, but DC grid following. So they basically create a stable AC voltage here, but they require another device to stabilize the DC voltage. And the first challenge, like from a very high level perspective that come up here, is that in a modern system, you will need kind of both of these controls to operate. So one of the examples would be here is a wind turbine. The way this typically works is that with back-to-back converters is that you're following the AC grid here, and then this converter creates a stable DC voltage here. And then that converter here is just controlled to basically keep the wind turbine at the maximum power point and feed power into this infinite DC bus that you'd created here by means of this converter. In an HVDC system, similarly, you would, if it's a point-to-point HVDC link here, and let's say we have a main kind of onshore grid and an offshore grid, what you would typically do is you would use an AC grid following control here that is forming the DC voltage here, so creating a stable DC voltage on the HVDC cable. And then the offshore one would be exactly opposite. It would assume that, oh, this DC cable is actually an infinite DC bus. Let me turn this into a stable AC voltage. And on the face of it, that seems reasonable. But if you start to look into this, you will quickly discover cases where, first of all, it's non-trivial which kind of which roles to assign to which converter. And the second problem is that if you look at this kind of wind power application here, or this HVDC application here, that you may have to update these roles here depending on weather, day-night cycles, seasonal aspects, depending on which side here you have more flexibility on to actually control the DC voltage. And we have some early results that I'm not going to go into further detail here, but what we also notice is that basically just creating an assignment where there's clear who's going to stabilize, let's say, the DC voltage and who's going to stabilize AC voltages does not necessarily imply that the system is dynamically stable. And once you throw kind of these questions into the mix, it becomes very complicated. So in a large-scale system where you have many converters here and you have to decide which role do they play, there are actually many assignments of these roles that result in an unstable system for most of the operating points. And then if you have kind of a system that is basically mixing AC and DC, then we have examples where it's impossible to find one of these role assignments here where all relevant operating points are small signal stable. So what this means is that as you shift operating points, you may have to redefine the roles of the converters here in real time. And that's, of course, a major obstacle and challenge to operation of future power systems. The second problem in general is that these PLL-based AC grid following controls are relatively fragile. There have been major incidents here, one in the US, where basically 1.2 gigawatts of solar PV dropped off the grid. 700 megawatts of this have been traced back to a problem in the inverter phase lock loop. Basically, the phase lock loop is operating under the assumption that the AC grid is just an AC voltage source with a perfect sinusoidal waveform. And that was not true here in this case due to line faults, and then these phase lock loops basically just dropped off. The second problem is often a bit overlooked in the literature, and it's that even if you take this perspective that the grid is an infinite bus and I'm a current source feeding into this, the voltage measured at the point of common coupling here is a function of the current in feed from this current source here. The PLL picks up on this and is trying to estimate an angle, and that angle goes into the control of this current source here. And you can actually create situations both in islanded and grid connected mode where this results in a positive feedback loop that just creates small signal instability. And the conditions under which this happens, they're relatively non-trivial and depend on the operating point, grid conditions, so let's say the strength of the coupling here. So ideally, we should strive to remove these PLL-based controls from the system, at least in my mind. But that obviously means we need some solution that doesn't rely on the phase lock loop, but still allows us to do the maximum power point tracking if we want. The final challenge is that the AC grid forming controls, at least the standard ones that you find in the literature today, they're designed under the assumption that whatever power source is feeding the power inverter has basically unlimited headroom and no significant response time. And it's also ignoring current limits on the power converter. So as it is right now, the AC grid forming behavior that the converter is producing on this terminal here is, as we were discussing, relying on an infinite bus here and not hitting any current limits here in the switches. Here's an example for what happens if you hit a current limit of the DC source, where then you collapse the DC voltage potentially, depending on what you're doing here. So a general problem here is AC grid forming control under converter and power source constraints. And this is what we will be looking at more towards the end of the talk. Okay, so in general, what we have seen is that we may want to use a control paradigm like this here when we want to do the maximum power point trackings, right? So we ignore kind of the grid, but we focus on extracting maximum power from our power source or stabilizing the DC voltage here. The AC grid forming paradigm that we've seen is basically you ignore what's behind here and you assume that somehow it can keep up with the power injection you're putting here, which is also maybe not completely viable. So what I want to propose today is a control that has a slightly different flavor here, and that recognizes that the power converter as such is not a power source that you can control arbitrarily, but that it's something that can translate basically between the DC and the AC side, and it needs to do this as best as possible. So to summarize this, we have basically a division into power sources that actually generate power. Think of a wind turbine or PV. And they often have a non-negligible response time, and they have limits on their power generation. The DC-AC voltage source converters that I'm focusing on in this talk here, they basically convert power between their terminals. They have a relatively small internal energy buffer only, which is this DC link capacitor here. And they're subject to current and voltage limits. And the problem is in both of the controls that we were discussing initially, we're kind of neglecting either the DC or the AC side, and thereby the power balance between the two is never really fully captured. So for the AC grid forming control, say, oh, I have a stiff DC voltage, let me turn this into a stable AC voltage. The AC grid following control basically turns a stiff AC voltage into a stable DC voltage. And what I will kind of dive into the details of now is an approach that is basically grid forming on both sides. So it's forming a voltage on either side here, and it's linking them together so that whichever side here has basically more flexibility can stabilize the other side. So the idea here is that you get bidirectional support. It doesn't matter which control what the setting here is where you're deploying this control. Whichever side is stronger will always stabilize the weaker side. So how are we achieving this? Here is, first of all, how this works for a synchronous machine, because that's a useful analogy here. So you see the rotating mass of the synchronous machine working basically as an energy buffer. Whatever power you're putting into the grid comes out of this rotating mass. And then you have your turbine governor system picking up on the rotating mass, slowing down and basically generating more power. So what you see here is that the drop in frequency basically implies more power injection from your turbine governor system into the machine, and that converts it and pushes it on through the grid. And what's interesting here is that this works even if you don't have a turbine governor system. If you think of a synchronous condenser, it's basically this thing here with the turbine governor removed, and you still get an inertia response, and you still get voltage support out of this device. Whereas if you were to use a grid forming converter control, let's say you put group control on it or virtual oscillator control, and you cut the DC source, it will just make everything go unstable. So here's the analogy in terms of a power converter. And you can see here the DC link capacitor, the power source, and the power converter. And the DC link capacitor essentially plays the same role as the rotating mass here. It's your energy buffer. So you get power in on the DC side, power out on the AC side, and this is your energy buffer. And we modified group control like this. So we basically added a DC voltage term here. And what this will do is basically it will account for the charge stored in the DC link capacitor here. So if your energy buffer here is getting depleted, what this will do is, in addition to the normal group response, it will pull down the frequency here. And this will kind of reduce its power injection into the system. And what's really nice about this control is that it's linking kind of frequency and DC voltage together. And if you now have a DC voltage source, a DC source here, that is responsive to changes in the DC voltage, that automatically stabilizes frequency. And in particular, this now has the same properties as the machine here if you remove just the turbine and the governor. So here, even if you have no source here, or it's operating at the maximum power point and it's not really responsive to the DC voltage here, well, in this term, you will control the DC voltage through the AC side. And you can still get features like frequency oscillation damping and volt-var control. So turn this into something that is similar to the synchronous condenser. So a lot of the results that I will show in a moment, they depend on this formulation here. What we noticed in the meanwhile is that it's actually better to remove the power set point here completely and to go to this formulation here, where you see that this is just dependent on balancing the power between the AC and the DC side. So this is saying, if I get less power coming in on the DC side, then I'm pushing out on the AC side, also drop the frequency. And then we noticed, okay, but this is only useful for the lossless case. If you have losses for the converter, they also need to be accounted for. You don't really know what the losses are. So you can use this instead, where you take the derivative of the DC voltage. And now if you're a control person and cringe and is like, oh no, you cannot, derivatives are not realizable. Well, note that what we need to actuate the converter is the angle here. So you can actually integrate over this entire equation and just get this bit here. So this is how this is implementable. And I will now focus on these two controls and talk about their properties a bit. So first, on a very high level, both of these controls, they basically are very simple controls, right? You've seen very stupidly simple feedback equation. And they provide both the functions that you would typically associate with a grid following converter, namely the maximum power point tracking, and the grid forming functions that you would associate with a grid forming converter without switching between any control loops. So it's just these simple equations. And here's the way this works. So if you have a renewable source that is at the maximum power point, it will basically not respond to any changes in the DC voltage. And you will then basically, through these equations, control the DC voltage through the AC side. And this gives you a more resilient kind of approximation of maximum power point tracking control. On the other hand, if you have a renewable source that's below the maximum power point, so something you can see here, you would do this in a PV system by operating at a higher voltage, then immediately a drop in DC voltage results in an increase in the power injection into the DC side of the converter. And then, as we've seen before, basically DC voltage and frequency are now tied together, so that directly gives you frequency support. And what's really nice about this is that basically this whole zoo of different control laws that we have right now, we can potentially replace it with one of these control laws that you have seen. And we can also have a unified stability analysis framework where we don't have to keep track of different controllers. To give an example, here's a benchmark system that we constructed by basically taking two IEEE 9-bus systems, connecting PV to this, as well as synchronous machines with a turbine governor system and a synchronous condenser here, and interconnecting them through HVDC. And basically using standard controls available today, you would deploy at least 4 different converter controls in all of this. And then instead what we have done, we've just put this universal control that I've shown you before, the one with the power set points on all the power converters here. And this supports the entire spectrum from maximum power point tracking to kind of a full grid forming mode where you provide frequency support. And it's also passing on any grid support functions through the HVDC here. So just to give an example here, for instance, this PV1 here is operating at the maximum power point, and that's corresponding to the dark blue line here. And you see basically the moment you put a load step on the system, this doesn't really respond. Whereas some of the other devices increase their power injection, or here, this is the HVDC, it's decreasing what's flowing across the HVDC. Here's a second example where we're using modular multi-level converters for mixed HVDC and HVAC systems. So you see here 3 AC systems connected through 2 DC systems. And a modular multi-level converter has a few more degrees of freedom that I don't really want to get into too much detail here, but basically you can control the voltage at the AC and at the DC terminal, and you have an internal energy buffer that you need to take care of. And again, we've deployed this energy balancing control where you take the difference of the kind of the state of charge of your energy buffer to where it should be to control both the frequency here and the voltage here. And again, in a standard setting, you would have to mix at least 2, probably 3 different controls to make this work. And here you can just put the same control on all of them and it works fine. And it's actually far more resilient to open circuit faults and loss of units, for instance, to contingencies like this. And what's relatively interesting is in this example, you can also show how to fully dispatch these things despite not having any power set points in the converter control. But the really big advantage of this, in my view, lies in the stability analysis. And just to give you a kind of a brief idea of what this looks like is, so here, we are basically now treating these power systems as something that has an AC network, which you would see in red here, and potentially DC network, which is shown in black here. Then you have these red nodes here in this graph, which could be, let's say, synchronous machines or a synchronous condenser. Black nodes here are just DC nodes, so that may be, you know, the terminal where you've attached photovoltaics. And then we have conversion nodes, which are these red-black objects here, which convert between the 2 worlds. And on the conversion nodes, we're basically deploying these universal controls that I've shown you, these dual port grid forming controls. And then we have a library of different devices here. So all of this is small signals. So we used the DC power flow approximation for the AC network, similar approximation for the DC network. The power flow depends on all the different node voltages here. And then we have simplified synchronous machine models, turbine governor models, DC node charge equations. For the converter nodes, it's basically the DC link or internal energy storage that you keep as a state. And then we also have DC power sources. And the crucial ingredients here is that we have this approximate power source model, which basically has the characteristics, for instance, here for a turbine, where it's a low pass filter, and then here you have the governor gain. But in a linearized framework, like even PV and wind power, they roughly fall into that category here. So many power sources can be approximated by this in the sense that they will have some sensitivity to a change in the DC voltage on their terminal and some low pass filter type behavior. And what we get is that if you put this dual port grid forming control on each of these converter nodes here, basically what you need is a sufficient amount of power sources that have a non-zero response to either DC voltage deviation or frequency deviation. And then there are some further restrictions on the topology, which are a bit too complicated here to explain here at the moment, but they're not really putting very strong restrictions. So they're along the lines of, you should not put two synchronous condensers onto the same bus in a power system. And using this, you can kind of prove now stability, including at least a rough approximation of the power sources and the DC side of the power converters and any kind of flows on the DC side. So just to give an example here, this bit here of the graph, for instance, could model, these could be wind turbines. So the machines are wind turbines. Those would be converters turning this into DC, then a DC collector network, and then you have another converter turning this into AC. So in all of these things, at least kind of in a reduced order, small signal type of framework, we can capture them and give stability conditions for this. So if you're interested in this, you can see this preprint on arXiv here. So before moving on, here's one of the things I have not talked about, and this typically comes up in all of these presentations. Okay, so what about inertia, right? We're losing inertia in the system, and what everyone keeps telling us is that our frequency response to a load step, as we decrease the inertia, it will do something like this here, right? And I was telling you that, okay, under these control laws, you're basically exploiting the energy buffer of the power converters, and that's more or less negligible. So let's understand what's going on here and what the role of inertia in today's system actually is, and why do we need it. So if you look at today's system dynamics, they are often described kind of using the second order equation here, which comes from the machine that you see here. And crucially, inertia here is a buffer of energy. So if you have a load step here, you're basically taking energy out of the rotating mass, and then this turbine here, which is very slow to respond, will slowly replenish kind of the energy in here by feeding in more power. So this is basically what these equations here tell you. You have the T here is the time constant of the power source, and then this will tell you that it's responding to frequency deviation. And it's true that if you drop this, reduce this inertia constant here, this is what you're getting. But this is not actually happening in the system if you use these universal controls and you transition to a system that has more renewables. And to see what's going on here, let's rescale time here by this turbine time constant T. So if you do this, you get these system dynamics here, and you basically, on this normalized time scale, you have not really changed the lowest frequency, right? So by stretching the time axis, I'm not changing where this minimum here is happening. And now you basically see that the crucial parameter here is the ratio between how big your energy buffer is versus how slow the turbine here is in responding. And long story short, it can be shown that the frequency nadir, so the lowest point that you're getting to here, basically just scales according to this ratio between inertia and turbine time constant. And the turbine time constant as such is basically just controlling how fast you get to this nadir here. So basically, the ratio will shift this pointer up and down, whereas the turbine time constant will move it left and right. And now if you consider going to a system that has more renewables interfaced by power electronics, you would see that the time constants that model these things, they are orders of magnitude smaller than that of a traditional turbine governor system. So for a steam turbine, this time constant T here, maybe 7 seconds. If this would be photovoltaics, it would be 10 milliseconds. If it's a wind turbine, depending on how much stress you want to put on the wind turbine, it's maybe 300 milliseconds. So if only the ratio here is relevant, you'll see that as we go to faster and faster power sources, we need less and less of an inertia buffer. And we're actually going to be fine without inertia emulation. The only problem here is that the maximum rate of change of frequency, so basically how quickly the frequency drops here, that scales linearly with the turbine time constant, but that's more of a local property. So if you're looking at the frequency at a machine bus, it depends on the turbine time constant and inertia of that machine. So again, if you retire it, you take it out completely and you will not suffer big consequences. The consequence of this is that Rokoff at the inverter buses is no longer kind of a meaningful metric to set up your protection system. Okay, so the message here is that because we're going to faster and faster power sources, this loss of inertia is not actually a big problem. The much bigger problems are interoperability and these universal control paradigms that hopefully support all of these functions. So with this out of the way, let me kind of try to shine a light on a more significant problem. So you can see that these universal controls that I was pitching, they can potentially be deployed kind of on, let's say, any number of technologies. I mean, I've used HVDC and PV as an example, but we are now also looking at how to apply this to wind turbines and so on, and it's looking fairly promising. The big problem is this third challenge that I was mentioning before, the converter current limits and potential limits on the voltage that you can modulate here. And in the standard control architecture for two-level voltage source converters, this is handled as follows. You have your grid forming reference dynamics here. So this is where you provide an angle reference and a magnitude reference based on power measurements or measurements of the DC voltage in this paradigm that I showed you. And then you have underlying voltage and current controls that try to track this reference here. And the way this is typically, the current limiting is typically handled is that you put a current limiter in the middle here. And the problem is this basically, when this becomes active, these two control loops here are cut off, and the result is just instability of your system. And there is a bit of a bigger story here in the sense that they can no longer emulate the behavior of machines because converters just don't have that overload capability. The specifications that you will see emerging in grid codes, they're basically on a case-by-case basis, and they specify the current injection by the inverter. So they say, oh, you know, if there's this type of fault, then you should inject that and that much, I don't know, negative sequence current. And this is inherently tied to the idea of controlling the converter here as a current source. But all of these things that we were doing on grid forming controls, they basically have the aim to not control this as a current source. And that gets me to the bigger problem here is that there is a lack of specifications for the grid forming response to faults and overload. And the last bit I want to talk about here is kind of a proposal as to what we should be looking at. So the main idea that I'm going to pursue here in the next two slides is that I'm claiming that what we should be doing is we should all agree on these grid forming dynamics group, this universal control that I was showing you, whichever one you like. But then the way to handle protection, in my mind, is that you try to track kind of these grid forming reference voltage as closely as possible without violating the converter limits. So if you have to deviate from the grid forming dynamics as such, you kind of want to know what's the least deviation so that I don't fry the converter. And here's a bit of an example for this. So let's use group control as an example. And you see here that I added two inputs here that will modify the frequency and the voltage magnitude. And under normal operation, that's not needed. So you have your operating point here, and then this control and the circle here is basically, once you go outside of the circle, you violate current limits. And you see the vector field pointing in. So what this means is that the standard group control under normal operating conditions, it will always kind of steer you away from the current limits here and into kind of a nice operating region here. But now if you were to apply this to a system where you have a voltage sag, then you see here these blue lines are the original kind of group control vector field, and it's pointing outside of the constraint, meaning that if you were to start here, then you would immediately try to bring up the voltage, and in doing this, you would exceed the current limits of your converter. And then what you want is to go in that direction here. So to follow this blue arrow as closely as possible while staying inside of the constraints. And this is a bit difficult to explain in continuous time. So let me rewrite the group control here in discrete time. So this is what you would be getting. And you see here that the angle at a particular point in time, oh, sorry, there should be a -1 here, is a function of the angle at the time step before, and then plus all of your discretization here from these group dynamics. And now you can wonder, what's the least modification? So what's the smallest adjustment of frequency and voltage magnitude here, so that I will not violate the current limit here? And the way I've written it here is an optimization problem. It cannot be solved, but the good news is that you can approximately solve this based on local information only. So without going into too much detail, you can basically find the following expression here. So you see there's another dynamic state here. This is basically integrating the constraint violation. And then you get two feedbacks like this here. And that will basically steer or kind of change the group dynamics here to stay within the constraints. So just to give an example for how this works, here's the standard approach to droop control. So this is your current limit. The system is connected here to, so the converter is connected to an infinite bus. And we have this switch here to create a voltage sag or short circuit current, a short circuit fault. And you see again in the nominal operation, this constraint is never active. So if you start on the boundary of this and the equilibrium point is in the inside, it will steer you here. So the moment we put a fault on the system, the voltage modulated by the converter would have to live here to not exceed the current limits. But droop control will just steer you outside. And then even if you clear the fault, well, it basically just keeps going and you will never come back here. Whereas this droop control with this kind of modification that I was talking about on the slide before, it is basically steering you to the nearest point within the constraints, which would be here. And the fact that it's not jumping directly here is due to the fact that, as I mentioned, that you can only approximately solve this optimization problem. So you end up here, and then once you clear the fault, it will just basically steer you back to this nominal operating point here. And that has fairly nice properties. Okay, that's it from my end. I'm happy to take any questions.
Terrific. Thank you, Dominic.